Yes.
With Maria. Okay.
Yes, we can.
Good.
Yes, yes, yes.
Good.
Sorry, yes.
Good. Okay, so welcome to join this talk, so organized by EAG Young Professional Community. So my name is Xing Wang, and also I'm the member of EAG Young Professional Community, and also I'm your host today. So today we are very happy to invite Dr. Gabriel Rizzuti, and he's going to give a talk about what scalable and sensitive quantification for seismic inverse problem with deep learning. And the agenda for today, next screen, yes. So first of all, I will just give a brief introduction about EEG Young Professionals community, so about who we are and what we do, and also what we are going to do. And most of the time is, so Gabriel will give a talk about sensitive quantification with deep learning. And if you have any questions or any comments, please feel free to ask, and there will be the Q&A session, and we will try to address them after the talk. And the fourth part is the closing part. So about who we are, so we are a network of young professionals age 35 or below who are interested in sharing or discussing any advice. We are trying to bridge the industry and academia and also the people from different places. And we established in 2013, and this currently have more than 2,000 members. And these are the EEG Young Professional community members, so from 2024 to 2026. And so Bridge is a chair, and also he's also with us in this talk. And I also saw some Carrie, and she's also here. So as you see, currently we have 10 members. And so for the audience, if you are interested to join, and please free to reach out. So about what we are doing or what we already did. So we are trying to organize special sessions in different conferences. For example, in the previous EAG annual conferences, Carrie and myself, we organized a session about young professional with energy transitions in this kind of topics. And we also have the EAG mentoring program. And I believe Maria, she reminds me that the registration is happening soon. It's in October or September. And also we have the educational and also networking events, such as this kind of YP webinars. And of course, we have the news, career advice, or vacancies. So something like that. So what is the mentoring program? So mentoring program is a 1-year career development exchange process by pairing the mentors and mentees, and they're trying to cover different kinds of aspects. So for example, the career and personal development, or you want to transition from industry to academia, or academia to industry, or different kind of projects. And or you want to talk about some like technical or like soft skills improvement, so you can find it in the mentoring program. And slides, yeah, obviously we have very good numbers, and if you can see the chart over there, so most of them they are students. If in the audience there are some students, and of course there's like mid-career professionals, and feel free to join and also reach out. And here are some upcoming activities in the Near Surface Conference, which is in Tuesday, 9th of September at 2 o'clock. So Bridge, I believe, so he's going to organize one session. It's called Beyond the Horizon, Next Breakthroughs in Near Surface. So this is one of the upcoming activities. And also in the upcoming GATT conference, which is in Rotterdam, I think it's 29th October, we are also organizing one session called The Role of Young Professionals in the Energy Transitions. So if you happen to be in those two conferences, please free to drop by and say hello or listen to our sessions. I think there will be a lot of interesting ideas and also discussions there, and you won't regret it. So, and of course, if you are interested in joining the LinkedIn community, please feel free to scan the QR code or just simply type EG Professional in LinkedIn and you can join us. And okay, so that's the main part. So before we officially started, and I would like to introduce Gabriel. So Gabriel Rizzuti is a senior research geophysicist at Shearwater Geoservices, and his research interest most focus on seismic inverse problem, with emphasis on numerical modeling, full flow inversion, and deep learning-based uncertainty quantification. He has a background in pure and applied math and holds a PhD at Delft University of Technology, and he worked as a research scientist at Georgia Tech and Utrecht University. Gabriel, so the floor is yours. I'm going to unshare my screen.
Yes, okay. So I'm going to share my screen. Okay, so Tishin, let me know if you can see the entirety of my slides.
No, we cannot.
Okay,
No,
try
yet.
again. Again,
There you go. Yes, we are seeing your screen. Yeah, perfect. Good.
perfect.
Please go ahead.
Thank you very much.
Thank you.
Yes. Okay. Well, let me start first by thanking Tishin, Maria, and also the rest of the team at this younger professional community. Yeah, and basically giving me the opportunity to talk about a topic which I'm very passionate about. So yeah, you heard my little presentation about myself. My name is Gabriel Rizzuti, and currently I'm a senior research physicist at Shearwater Geoservices. And today's topic is about scalable uncertainty quantification with an emphasis on seismic imaging problems. And the type of solution that I want to discuss today are fundamentally enabled by the latest developments in deep learning. Okay, so yeah, I organized the talk in this way. So this is the agenda. I'm going to start with a relatively formal introduction on, what we mean by uncertainty, just to make sure that we are on the same page. Okay, so what it is and what scope, scope it serves. Then in the second part of the presentation, I'm going to discuss a little bit more technically how we can solve for this problem, which is, of course, it's not a new topic. It's something that occupied our community for a long time, and it's not an easy problem, right? So I'm going to start by, explaining a little bit some solution based on MCMC methods that were the de facto standard for this type of techniques. And then I'm going to talk about our proposal, which is based on something called variation inference. And in particular, deep learning variation inference, where the deep learning architecture we're going to use are relatively special in the sense that they are invertible. They have other nice feature to it that make them very nice, let's say, for uncertainty quantification in particular. Okay, so I'll talk all about that, and of course, at the end, I will discuss some application related to ultra-high resolution seismic for offshore wind farm, and then I'm also going to discuss a 3D example at the end. Okay, so hopefully that sounds good. So yeah, I guess question that will be at the end of the presentation. Yeah, I mean, I would be okay also answer the question live, but that's fine. So let's start with this introduction, right? So what do we mean by uncertainty? So whenever we are trying to peer into the subsurface, right, we want to have a clue clue about what the subsurface looks like, we need to contend with, I would say, two types of ambiguity. The first one, which is exemplified by this first diagram here, I would characterize as a rhetoric ambiguity. And this, it works as follows. Let's assume that we have a relatively precise knowledge of how the subsurface looks like, which I denoted here as X. X, especially in the context of imaging, may represent acoustic impedance or other material parameters like velocity, density, or whatever. So even if you have a precise picture of that, how X looks like, it will not observe the same seismic data at the surface exactly with two different experiments, even if you replicate exactly everything. Okay, and that's due to the fact that the dynamical system underlying the subsurface is inertly stochastic, so there is ambient noise, which might be a structure type of noise, or there might be unstructured noise, maybe related to the measurement errors. Therefore, you get data contaminated by noise. Now, of course, you never really have a precise picture of the subsurface looks like. That's actually your problem. You only have access to single observed data, typically. That data denoted with the letter Y. So on top of this, say, ambiguity, the rhetoric ambiguity that comes from noise, then you also have to contend with another type of ambiguity, which is maybe characterized by the word epistemic. And that's mostly related to the fact that you have limited source-receiver acquisition. For instance, you have only one-sided illumination of the Earth, but also you have a limited number of sources, limited number of receivers, and so on and so forth. And that also contribute to increase the ambiguity and then make it so that you basically there will be many different models of the Earth that will explain in a way equally well the data that you collected. Okay, so sensoric quantification is essentially a way to characterize this ambiguity. So at the heart of the proposal that we are going to discuss here is there is a switch from a deterministic perspective of the Earth, where only a single model is proposed. But as we discussed just now, then of course a more complete solution would be actually a full characterization of not just one but many models that will fit the data, right? And then we can describe that mathematically with a probability, and in particular with a probability density function, which is displayed in this right-hand panel. Okay, so the solution in practice for uncertain quantification would be like being able to sample from this distribution, or maybe characterize the distribution with summary statistics like average standard deviation and maybe higher order statistical moments, something like that. So I would say there are three main steps to uncertain quantification. The first one we just discussed. So you have to identify, of course, the source ambiguity, like measurement noise, incomplete data, and so on. But also you have to identify the source of certainty, right? So the contrary of ambiguity, and that comes at least in the Bayesian setting by means of the so-called prior. Prior basically is a way to discern what are the model parameters that look physical there and then are desirable, right? So it's a way to weed out models that don't look really like the Earth. And so in the second part of the talk, I will describe a little bit more technically what we choose for each of these items. But we're going to make use of very standard ingredients, so nothing that's surprising there. The second part is the, I guess the center of this talk, which is how you define this uncertainty, essentially. Here, you have several techniques. We're going to focus on one in particular, but let's say you can choose in this step whatever you prefer. And then the third step, which is equally important, is actually coming with a decision-making process, right? So how do you use the results that you get by quantifying the uncertainty? Right, so you basically need to be able to answer a question like, shall we drill in this location or rather that location, or maybe shall we stop injecting CO2, or maybe what is the best layout for an offshore wind farm? This type of question, right? Another interesting question that I'm not going to touch today, but it's also interesting. I use a lot of the frameworks that I'm going to describe for uncertainty, which is experiment design. It's a little bit of a different question from the way that I pose the uncertainty framework. And it's basically experiment design asks what are the best allocation sources and receiver, for instance, in order to minimize the uncertainty, right? So it's a slightly different question, but still related to the framework that I'm going to discuss. So this third step is very important. As I mentioned, we're going to focus on the second step, but in future work, of course, this third step will be, of course, very, very important for us as well. But we're not going to discuss that in detail today. Okay, very well. So that's a warm-up phase now, and we can now start talking a little bit more in detail about the theory and mathematical details that underline our own proposal for solving for uncertainty modification. Okay, so let's start easy again. So this is the Bayes theorem, right? So I assume that most of the audience is relatively familiar with this formulation. Basically, we are characterizing mathematically the target distribution of interest, which is called the posterior, defined to be proportional to the multiplication of two terms. The first one is the data likelihood, which describes essentially how the data formation process happens, right? Having perfect knowledge about the subsurface X. And the second term is the so-called prior that I just described, which regularize the problem and has the role to identify, before measuring the data, what are the likely samples, basically. Okay, and then again, the goal, we want to characterize this posterior, although we have this, let's say, theoretical formulation, that's not enough. We want to be able to sample from this posterior. We want to be alternatively able to characterize it by means of a conditional mean or standard deviation or whatever. Okay, so that's our goal from a mathematical point of view. Okay, so in our field, typically the de facto solution for uncertainty modification is based on Markov chain Monte Carlo methods, MCMC methods. In essence, MCMC methods consist of exploring the space of the unknowns X by traversing the space in a sort of a stochastic fashion. They consist in producing a sequence of samples X, and from each X, from each, let's say, current estimate of X, you can produce the next subsurface description by randomly perturbing that's the state, essentially. And there are different ways to do this. Here I'm just listing two relevant examples that you already might be familiar with and are actually relatively popular. The first one is the advanced dynamics, which use the gradient or posterior distribution to move around essentially. And there's also a step reject step, right? So sometimes, this stochastic step give you a sample which is not very realistic. Then you can decide if you accept it or reject it. And another popular method is also HMC, Hamiltonian Monte Carlo, which works in a similar fashion. That's slightly different in the sense that the stochastic path now lives in the phase space. It's different space, but the idea is relatively similar, right? So we have this stochastic sampling of the effective support of the posterior distribution. Now, these are methods that have been investigated a lot, but they have this important downside to them, is that they will not scale very well, especially for large dimensional problems, and especially in 3D, right? That's at the end what we are actually interested in. So for today, I'm going to focus on this alternative, which is called variation inference. And variation inference is a reformulation of certain quantification by means of optimization problem. So the gist of it is that you need to come up with some, let's say, approximate model that I'm calling here p theta. And p theta will be some candidate distribution that will try to approximate what you're interested in, right? So there's posterior distribution. And theta will be some parameters that define basically the shape for this density function. Now, since you want to transform this in an optimization problem, you also need to have a way to measure the discrepancy between the candidate distribution p theta and the target distribution. And then once you have that, of course, you have to you can minimize over the parameters of this distribution. Okay, so that's it. That's in essence variation inference, and specifically for deep learning, for the deep learning incarnation of variation inference, we are going to represent this distribution by means of a neural network. Okay, so you might have guessed that already. The way it works is relatively straightforward. Essentially, you have some latent space distributed to a distribution that you know, from which you know how to sample, basically. So these stochastic inputs will be fed to the network, and if the network is tuned appropriately, right, they will produce some stochastic outputs that will be hopefully distributed as the target distribution, right? So that's what we want to do. Okay, so before moving forward and describe more in specific this deep learning-based variation inference, I want to draw your attention to some of the comparison that I put in this table. So MCMC methods have nice theoretical guarantees in the sense that if you have infinite compute resources, essentially you're guaranteed to sample from your target distribution. Okay, so in that sense they are exact. However, as I already said, they do scale very badly, right, for high-dimensional problems. Again, that's mostly due to the fact that typically consecutive samples are highly correlated within each other, right? And that means that you need a lot of iteration to converge. Then if you think about FWI, for instance, that means that you need to spend a lot of resources for this process. There are also other downsides that are also important. I think it's important to mention that here. So this one is related to memory complexity, right? So in order to describe your posterior distribution, you basically need to store all the samples that you generated in the chain. And then if you think about 3D, then it means that you need to store a lot of 3D samples. That may be, let's say, awkward or maybe difficult to store actually in memory. If you need a new sample, then you're forced to rerun the Markov chain, right? And then, of course, that still requires even further computation resources. And the last point is the fact that these methods are relatively inflexible, in the sense that if you're interested in solving, let's say, a problem which is related to some other problem that you solve with MCMC methods, there is no simple way, basically, to transfer those results to the new problem. On the other hand, Bayesian inference only provides an approximation, right? So you can regard that as a negative. However, if you choose a network that is powerful enough, then maybe this point is less of an issue. Time complexity, I deem it more scalable, let's say, with respect to model parameters. Of course, training a neural network is not an easy feat. However, due to the fact that you are able basically to transfer the result of the training of the network to not just one problem, but maybe several problems, this training cost can be amortized considerably. And then that's basically why I put time complexity in yellow, because it's more manageable, amortized. Techniques will allow you to cut the costs in some way. And then, of course, you only store the network parameters. You don't need to store the outputs. Whenever you need a new sample, you just evaluate the network on the fly. That's going to be easy. And then, yeah, this point I already described, you can use warm start, fine-tuning, transfer learning to learn across tasks. Okay, so hopefully I convinced you that this is the way to go. And now we can talk a little bit more in detail about our own proposal. Okay, so I already mentioned normalizing flows. These are specific neural networks that have two main features to them. So the one is invertibility, right? So whenever you have an input, you can evaluate the network and get an output X. But you can also evaluate the inverse of the network with a normalizing flow and then get the same inputs, okay, at least up to machine precision. The other feature is also very important, crucial, I would say, especially for uncertain quantification. It's the fact that for whatever output X you have from the network, you're able to compute in an analytical way the probability density function associated with that sample. Okay, that's thanks to the invertibility first, but also the way these networks are constructed. Okay, then you can basically resort to the so-called change of variable formula, right? And then that allows you to characterize analytically the likelihood of the outputs. Thanks to these two ingredients, you can train your uncertain quantification problem by means of the Kullback-Leibler divergence, that is known as KM in this case, which is defined as the average of the ratio of the two probability values. Another important point that I also like to stress, and it's particularly related to normalizing flow, will not be true for a generic neural network, is depth-independent memory complexity. That means that for a generic network, essentially, whenever you use backpropagation algorithms, you need to store also all the intermediate function, intermediate activation function corresponding to these nonlinear steps, right? That's particularly problematic for a very deep network and especially for 3D inputs, because then you need to store a lot of internal states. Then in 3D, yeah, that would be quite hard to achieve. But since our networks are invertible, essentially we can recompute these intermediate steps and then avoid all this checkpointing type of alternative solution to the propagation problem. Okay, so this is another feature that is going to allow us to scale this problem to 3D. Okay, so before moving on, I want to just briefly describe just simple example of normalizing flow, in this case the coupling layer. The way it's defined is relatively simple. So you have an input X, you're going to split it into parts, however you want. You don't do anything for the first part. So basically you define the first part of the output, C1, to be equal to X1. And the second part of the output will be defined according to this formula, which is just a fine transformation on, with respect to the input, the second part of the input. And here the scaling factor and the translational term can be defined by means of very general neural network. There are no restrictions on the type of neural network that S theta and d theta are. Can be as complicated as you want. And the nice thing about this is that you can compute the Jacobian, right? And this transformation. And the way it's constructed, this corresponds to a lower triangle structure for which you can compute the determinant. And then you can, go back and then compute this likelihood estimation according to this formula here. And it's a more complicated version of normalizing flow. You just need to put all these ingredients together by chaining. And there are also other type of normalizing flow building blocks, but let's say for the moment that should suffice just to give you an idea. So this is a slightly more sophisticated version of the network we want to use in our examples, which is based on just a multi-scale decomposition. It's a very old trick, right? So in seismic imaging, we use it all the time. Basically, that means that you decompose your problem on several scales of coarseness, and then you start solving, for example, your deterministic problem in FWI on the quarter scale, and then you add details sequentially, right? So then you move from coarse scale to fine scale. The idea being that lower dimensional problems are easier to solve, and the same is true for solid quantification. And we bake this behavior, this multi-scale behavior, in the architecture of the normalizing flow that we want to use. Okay, so at the end of the day, right? So the inverse problem that we want to solve should be at least familiar to any practitioner. So you can write down explicitly, right, the Kullback-Leibler divergence, which consists now in two terms that I highlighted here. The first one is the called reconstruction error, which essentially looks like your conventional deterministic objective function. The only difference being, the main difference being that we replace the unknowns x with outputs of the network, right, g theta. Then, of course, we have to average over the inputs of the network, right? So this term here will allow basically the output of the network to describe the data y. In the second term, you can regard this as a regularization term, the entropic term, which will try to counteract, in a way, the behavior of the first term, right? The first term will try to put all the samples, let's say, in the same place, because they will try to fit the most likely sample, right? The maximal posteriori solution to your problem. But that's not really the desirable solution because, you end up with a Dirac delta function, which will lack a lot in terms of sample diversity, and ultimately that's not what you want. And the entropic term will force all these particles to explore as much as possible your unknown space. So in other words, this will avoid the so-called mode collapse. The pseudo algorithms, it's also relatively straightforward. So we run a bunch of iterations, and at each iteration, we have to randomly sample some input from the latent space. Let's say certain batch C1 to Zm, for instance. Of course, you have to know how to sample from this latent distribution, but that's the hypothesis that we made in the previous slides. Then, of course, you have to evaluate the network. And then, similar to deterministic inverse problem, you have to compute the gradient with respect to your projective function, which is the gradient with respect to this first part here. And then you have to backpropagate those gradients through the several networks, the several layers of networks. Also consider this extra term, the entropic term. Then you end up with gradients with respect to the network parameters, and then you can finally update network parameters according to gradient ascent, Adam, or whatever update rule that you like. Okay, so at the end of the day, I would say a very simple algorithm. So just one note before moving on with applications. So I never mentioned so far training data set, right? So we only have a single observed data. So you might then classify this type of approach as sort of an unsupervised machine learning technique in a way, but at the end of the day, this is just a good old problem, very standard. The only difference is in the way of the techniques that we choose to solve this, that are based on machine learning techniques and methods. So slightly bit different than your conventional machine learning exercise. That's all I'm saying. Okay. So this would be maybe a good time for question, but so we said that we are going to do that at the end. That's fine. So let's now talk about applications. Okay, so in this presentation, we're not going to be very sophisticated in terms of the type of inverse problem we're going to tackle. And we're going to perhaps choose the most simplistic or simple inversion problem that we can think of, which is post-hoc seismic inversion. So the unknown x would correspond to acoustic impedance, and the data will be post-hoc data. The forward problem, forward modeling operator is super simple. It's just time convolution with respect to a wavelet, which is going to assume that is known and fixed throughout. There's also, of course, a derivative with respect to the time. So we're so the vertical dimension of x is going to be time. So we're going to do time domain inversion. Okay, then whatever prior you're going to choose, then this is how the procedure is going to look like. Just a couple of mentions about the prior. We're going to make use of relatively simple handcrafted prior based on Gaussian smoothing or maybe TV regularization, for instance. So again, something relatively simple, but in principle you could use something more sophisticated, maybe based on learning some prior distribution. That's also a possibility, but let's say in the application I want to show, we stick to simple ingredients. Very well. So the first application is ultra high resolution data. So this data was kindly made available by German authorities. So this would be our data. This is the greatest stack that I'm showing this slide. I'm not going to discuss the way this image was formed. Then I will urge you to maybe have a look if you're interested. Of course, in this reference by a colleague of ours that explained a little bit more in detail how all the processing step that produced this image. There's also this this other reference that from another colleague of ours that you can also check. So the tricky part about this data basically was the ghosting part. But okay, let's assume that we have this data wide, and then we are going to focus on the relatively small portion of this full migrator stack, which I'm going to show in the panel on the left. Then we also need to have, of course, some clue about the acoustic impedance on the right, which is a very slowly varying version of the acoustic impedance. Okay, so I'm going to show right away the results that we have. So these are random samples that have been chosen from the output of the network by randomly evaluating the network. So these are not particularly, let's say, nice to look at, you might say, relatively noisy, but you may, let's say, consider each of these samples as, in a way, a solution to your deterministic problem. And then if you look carefully, you may see that there are maybe a lot of features here that may seem structured in a way, but if you compare it with other samples, those features disappear, right? So that's maybe a way to say that essentially you should not basically trust too much a single sample, right? So you always have to consider the result of your inverse problem as an ensemble of solutions, right? Okay, so that's maybe one way to look at, but of course you might need basically a better way to assess the uncertainty, right? So this is perhaps okay, but not very helpful at the end. So what people do in order to give a more concise description of uncertainty is by means of summary statistics like conditional mean, standard deviation, or other statistics, right? So here, for instance, I'm showing the conditional mean on the left panel, and showing the standard deviation in the middle panel. So here the color map displays in the bright colors basically all the regions of your model where the samples vary a lot, and that corresponds mostly to regions where we have interfaces, right? So that's sort of qualitative assessment that you can make with standard deviation result. The last panel, maybe need to explain this a little bit further. This is the conditional covariance, and you can regard this as a column, essentially a column of the covariance matrix, right? Which is a picture in image in 2D at least. You can see that I denoted with this yellow cross a certain reference position, and the meaning of this bluish cloud here is that the nodes, all the points that are positively correlated with that reference grid point. You can see that correlated points are distributed nicely and tightly around this the reference grid point, because the problem I'm trying to solve is relatively local, right? So that's something that you would expect. Okay, so this is nice. It is a way to summarize the statistic, but also you have alternative way to do that I would argue are maybe more fit, let's say, better fit for, in particular, for ultra high resolution data, which is in terms, presenting uncertainty quantification in terms of credible intervals, right? So of course, like I'm dealing with pictures, right? So I'm trying to basically describe intervals by means of feature. That means I need to, for each interval that I'm considering, I need to show you two types of results, right? So for this interquartile range, I'm showing the 25% percentile and the 75 percentile. And a way, I guess, to interpret this is that the probability of your acoustic impedance to have values that fall between the two values, that is two pictures, for a fixed grid point, is more or less 50% in this case, right? If you are a little bit more conservative, and then you want to be, maybe you are a little bit more risk averse, then you can consider a wider range, which is the interdistant range, where basically you have probability of 80% of your acoustic impedance to fall between these two values, right? And then you can, of course, play around with this and then choose, arbitrary intervals, right? That's in essence what this this slide try to convey. And yeah, so last, just one last note, I mentioned multi-scale certain quantification. You can represent the statistical force ensemble, degree of coarseness, right? From coarse scale on the left to fine scale on the right. Okay, so before concluding for today, I want to at least show you a 3D example, since I mentioned repeatedly, scalability and 3D, and then I want to show you that we, at least for a relatively medium-sized problem, we can actually run these things in 3D. This is based on a synthetic data set, based on the CM model. You can see post-hack data on the left, and then you can see ground truth. Okay, so we have synthetic, so we have a pretty good way to know how the best solution should look like. And then, of course, we have a smooth background model on the right. Then I'm going to show you right away the solution, just in terms of condition mean and standard deviation, left and right, respectively. Same, qualitative consideration that we made for the ultra-high resolution model applies to these results, mostly due to the fact of the way we chose the prior. The regions that are more uncertainty correspond to the interfaces of your model. Okay, very well. So I think that we can nicely now go to the discussion and conclusion for this talk. So diploid-based variation inference via normalizing flow is feasible, at least for mid-sized 3D problems. All the characteristics and the features of normalizing flow are going to be very important in order to scale a certain quantification to 3D. Of course, we are not happy with this. With this size, right? So we need to tackle larger and larger problems. And then we will have to do that with, of course, Monte GPU training. So this to-do part I already mentioned throughout this presentation. We only consider very simple handcrafted prior, but of course you can think of workflows where you actually learn the prior, which is going to be more descriptive of your subsurface and maybe a preferred prior. Then you can also use this in combination to all the other things that define the techniques in this talk. Then you can, another thing that I should mention, that also, for each data, you basically need to pre-train the network. So you can amortize the cost by adopting, simulation-based inference, right? Then you can consider a whole range of data. Then you can train, let's say, one model for all this data, then perhaps transfer learn to some new, let's say, unseen data, right? That's a conventional way to do transfer learning. So this is a general framework, right? So I discussed acoustic impedance, but of course you can extend this to the elastic impedance inversion. Ultimately, what we want to do is tackle RTM or FWI. That's actually ongoing work. Of course, we need to also consider all the additional computation complexity, right? That is going to be very different than the simple example that I just showed. I only described imaging problems today, but there are the framework is very general, right? So you can adapt this to basically any seismic inverse problem that you think of, even considering processing application or other problems. Okay, so just a final acknowledgement to Invertible Networks JL, which is Julia package that we developed during my time in Georgia Tech, and also like to thank NVIDIA for the ongoing collaboration that we have. And I think that concludes my presentation, and we're now ready for some questions maybe. Thank you.
Thank you, Gabriel.
Okay, Gabriel.
I think that we have some questions in the chat. Let me read them for you.
Yes.
So Rinal says, how do I assess the accuracy of your results?
Okay, yes, that's a very good question. And a question that is going to be particularly relevant for, I think, nonlinear inverse problems. Okay, so now what we did in practice for, let's see. Yeah. So what we did essentially for validating for the sample that I showed is the following. So this slide basically is a comparison of some analytical solution with a certain quantification with our results. Yeah, the conclusion here is that we get results that are pretty in line with what we should get. Now, this analytical solution is possible, is available only because of the choice, the simplifying choice that we made about the assumption of the problem, right? So we are going to consider linear inverse problems with Gaussian priors, and in that case, then you have a way to actually characterize fully the uncertainty, right? And that comes in the form of a single mean and a single standard deviation matrix, and then you can compute samples in and other statistics in an analytical way, right? So that's why we can actually do this comparison and make sure that the results are in line with what you should expect. Now in 3D is going to be a little bit more complicated because, of course, computing this analytical solution is based on basically large matrix factorization, which is not very doable in 3D. Then in that case, there are still ways to do it. For example, by resorting to randomized and optimized algorithms, which is a specific way to produce samples that you might consider exact, quote unquote, from the posterior distribution by perturbing the data in a special way. So long story short, for this simple assumption of linear Gaussian, you have a way to assess your results. What I was mentioning before is that for nonlinear problems, right, for wave inversion, it's not going to be possible, and that question is still open. So I don't know exactly how we're going to accurately assess the uncertainty in that case. That's ongoing investigation. I would say in that case, you can only resort to very qualitative type of analysis, but it's going to be very challenging. So I don't have, in that scenario, I don't have a good answer, but we are thinking about it. I hope that satisfied the question.
Thank you, Gabriel. There's another comment into the chat. Dia says, in the case of the post-stack inversion, one will expect an increase of the standard with dip, but it was not clearly observed in the presented result. Does it suggest that they included prior threaded observations?
Sorry, I didn't catch the very last statement.
Does it suggest that they included prior threaded observations?
Yes, that's correct. So the fact that you don't observe increased uncertainty with depth is mostly because of the prior that we choose, right? So you might argue that a better, more realistic prior would be to encode, let's say, that's uncertainty in a sort of a artificial way in the prior, essentially. So that would be my suggestion. So that's basically due to the fact of how we formulated the problem.
Thank you, Gabriel. We have another question. How does the dimensionality factor in here?
How data dimensionality factors. So I guess in terms of computational cost, scalability. So I guess, I mean, of course, training will be the part that's going to be affected by the dimensional problem. For these simple problems like seismic inversion based on post-stack, the methods scale relatively well, relatively fast. So meaning that you don't need a lot of iteration in training, even for 3D problems. But that may change, for instance, for For more complicated nonlinear problems, like for waveform inversion, in that case, yeah, the issue is a bit more problematic, obviously. And even if we were able to run the same number of iterations that we did for this post-stack inversion, that would be too much. So we need to come up with different strategies, right, in order to be able to make the problem more scalable. And I'm thinking about source encoding, basically throwing everything but the kitchen sink in terms of techniques to reduce the cost, and then make the training as simple as possible. But yeah, the number of iteration of the training will depend in general on the dimension of the problem. However, this is way better than if you were to compare these techniques with MCMC methods, as I tried to describe in the beginning.
Thank you, Gabriel. Any other question from the attendees? Maybe you can turn on your microphone and ask directly to the instructor. Bridge, do you have any question or teaching?
Maybe that's
actually, we have missed one from Professor Sain, because he's also post-stack is, I think, the post-stack modeling and the inversion, is it done one CDP at a time? Is this how you are doing?
Bridge.
Yeah.
Sorry, I didn't get the question.
Yeah, the question is that is the post-stack modeling and the inversion is done one CDP at a time? So is it like being done each CDP, or how do you perform it?
Well, we have post-stack data, right? So we have that migrated stack. That's it. Yeah.
Thanks, Gabriel.
Any other question from the attendees?
Professor, we cannot hear you. Yeah, we can see you, but we cannot hear you.
We cannot hear you, yes.
Okay, other questions?
No, it seems that we don't have more questions. Teaching, do you have any comment, Bridge?
No, it was very good.
Yeah, so Gabriel, one more question before we close the talk. So in the recent conferences, we've also seen people start to use the diffusion model to do the uncertainty complications. So any comments on that? So what kind of benefit diffusion model can bring to us? So compared to the normalizing flows?
Yeah, so diffusion models are an interesting alternative. They have their own strengths and weaknesses, I would say. So diffusion models cannot use directly in the way that I use, so you cannot really, in a technical sense, minimize directly the Kullback-Leibler divergence, because they don't allow you to describe explicitly the density function associated to their samples, right? So you need to do something a little bit different. However, the nice thing about it is that typically they are more powerful generating model if you compare it with the normalizing flow. So it would be interesting actually to see what are the benefits if you were to use diffusion models. You may also need to factor in the fact that diffusion model may also be more computationally expensive. inference, right? So that's another aspect. But yeah, I'm also curious. I don't have much experience with those, but I'm interested.
Can I just ask a short one, because now it came to my mind? Because Gabriel said that you are using the stack, so I was just wondering, for this particular method, do you have to do some specific post-migration processing, or do you have to?
So like what?
Like any kind of like additional because you're using the stack, right, for the inversion.
Yeah,
So,
correct.
so particularly for this application, is it like, or if you have applied any kind of special post-migration, the post-stack processing, any kind of, or is it like just standard stack?
So not, I mean, for this example, not really, but you might, yeah, I guess you may also consider conventional, yeah, post-processing for the stack.
Okay.
But in this example, there was nothing particular that required mentioning. Essentially.
Thanks.
Okay, we don't have more questions or comments, so I think that we can close the webinar now. Thank you, Gabriel, for being here today. Thank you, Teishin. Thank you, Bridge. And of course, thank you to all the participants for being here today. Hope to see you soon in our future activities or even webinars. So yeah, this is it from our side. Good to see you all. Have a very nice rest of the day.
Thank you so much.
Bye-bye.
Thank you for having
Thank
me.
you.
Thank you, Ron.
Bye.
Have a good day.
See you. Bye-bye.
The same to you too. Bye-bye. Thanks.